extremely fortunate to have Juan Maldacena giving us 5 Loeb lectures. That'll be every day this week. And because of room scheduling issues, tomorrow and the next day we'll be over at the Science Center, and then we'll be back here from Wednesday on. I'm going to say a few introductory words about Juan at this first welcome, and I'll be quiet at the rest of them. I first met Juan in 1996 when I read an extremely interesting paper that he wrote with his thesis advisor, Kurt Callan, and I wanted to understand it better. And so I sent Kurt an email and got a reply from this unknown character, Juan Maldacena. And it was such an interesting and stimulating reply that I immediately invited him to come out to Santa Barbara, where I then was, and we started working together. And I guess we then wrote the first of 15. We then wrote the first of 15 papers over the intervening years, and I should say that having the privilege of working with Juan has been one of the great personal and intellectual pleasures of my career. Shortly after, I guess things moved really fast then, Juan and I came to Harvard together in 1997, and just a few months after arriving at Harvard, Juan wrote a paper which I think can only be described as astonishing, in which he showed that string theory was, or in some cases, completely equivalent to quantum field theory, and that two subjects that we had been studying for many decades were in fact really the same subject. And this opened a deluge of new insights into all kinds of areas of mathematical physics, also implications for astrophysics, condensed matter physics, and his influence has spread far and wide across many areas of theoretical physics, for which he's been honored by numerous prizes. I could mention the Sackler Prize, the MacArthur Prize, the Heinemann Prize. I can just go down random prizes. I know I'm not even sure if he got them or not, but I would assume he did. If I get one wrong. If I get it wrong, the committee better get to work. So the Fundamental Physics Prize. Without further ado, let's have Juan tell us about black holes.
Okay, it's a pleasure to be here. Thank you for the kind introduction. Today we are going to talk about black holes and what they teach us about the structure of space-time. Black holes are quite strange, and they have been a source of a lot of confusion. Already, classical black holes were a source of confusion. And
is your mic on?
I was told it was.
It's on? Okay.
So then I should take it closer. Hello? Now? Can you hear me better? Okay. So it took a long time to understand them classically, already in the classical theory. And we have some evidence for their existence as classical objects. And today we are mostly trying to understand or see what we can understand from the quantum mechanical point of view. Now, classical black holes. So the solution was found about 100 years ago. It's the simplest spherically symmetric solution of Einstein's equations with no matter. And this geometry, so you can find and you can write down the geometry. But instead of writing down the geometry, well, there is this nice picture of showing how time flows. So this is the flow of time. This is a clock far away, and this is a clock near a massive star, let's say. It goes a little more slowly. And the geometry tells us exactly how much more slowly it goes. As the star with the same mass get smaller, the clock's this redshift factor becomes bigger. So G00 becomes smaller, so the clock runs more slowly. And if the star is less than a certain size, it seems that there is a point, a surface, where the clock doesn't run at all. So in the beginning, this was called the singularity. It's not what currently is called the singularity. And people that Einstein, who created the theory of general relativity that predicted this, thought this was impossible, that this was the result of some approximation, and that in realistic cases, you couldn't have such a ridiculous thing. But it was later understood that black holes can form, and so you can have a star, and the star can collapse. And a convenient way to understand this is through a so-called spacetime diagram, or sometimes called Carter-Penrose diagrams, where you represent the whole spacetime in this following picture. So here I've suppressed two of the dimensions, which are the two spheres. The situation is spherically symmetric. We are considering a spherically symmetric situation, so we're not going to draw the directions of the sphere. So we're only going to draw the radial direction and the time direction. So the time direction runs vertically in this plot, and the radial direction runs along this direction. So very large radius, very far from the object, corresponds to this region. And the regions that are infinitely far away, they were rescaled so as to map them to a finite position here on the diagram in such a way that light rays move at 45 degrees. So if we have a point here, and we have a physical object moving forwards, it will move within the light cone, so within a line that is 45 degrees in this direction and 45 degrees in that direction. So here we see that the point where the time was stopping was this surface. It's an imaginary surface in the space-time called the horizon that has the property of separating the points that cannot send the signal to the outside from the points that can send the signal. So from a point here, we can send the light ray, and this light ray will reach infinity, so the region that is very far away. While if we're in the interior, that light ray will reach the singularity, but will not get to infinity. But what's important is that someone who is sitting here at the surface of the star just crosses the surface without noticing anything peculiar. So there's nothing special that happens here. And in fact, the metric in this region looks very similar to the metric of a collapsing universe. In fact, the interior looks very much like a collapsing universe. And you don't need a lot of mass to, well, if you want to collapse this, you can, if you have nuclear densities, you can collapse solar mass to an object that has a density roughly comparable to nuclear densities, and then it will collapse to a black hole. But of course, it doesn't have to be so dense. You can just take water, and you fill a large enough sphere of water, and that object will also collapse to a black hole. So if you fill, for example, a sphere of somewhat bigger than the size of the sun with water, it will collapse to a black hole. And the black holes at the center of our galaxy have this typical density of water. So they don't have to be extremely dense. And the fact that we have matter, which is normally not very dense, like gas or like nuclear matter. So here I'm calling nuclear matter not very dense. I will talk later what would be a more dense form of matter. But the most dense form of matter that we can have is typically nuclear densities. And because that's relatively low density compared to the Planck scale, we find that the black holes that we typically make are very, very big. In fact, if we have a black hole that collapses from fermions of mass m, so if you have a bunch of fermions, you put all these fermions, they form a big object. And their biggest density is roughly the interparticle separation, their Compton wavelength. That's how much you can bring them closer without increasing too much the energy. And you find that they will collapse to a black hole, which is roughly the mass of the fermion times this factor of m Planck over m. So m Planck is, well, g Newton is 1 over m Planck squared, and is a mass of order a microgram. Or in terms of Planck masses, so you see that there is this factor of m Planck over m. So the fact that black holes that are formed naturally in nature is due to the fact that the proton or the neutron are very light compared to the Planck mass. Okay? So that's why black holes that naturally form are so massive. And if we wanted to form a smaller mass black hole, we would have to concentrate matter to extremely high density, so much higher than we can hope to do. Now, as I said, nothing special. So the surprising aspect is that there is this interior vision, and we cannot escape from the interior. There is, of course, this curvature singularity in the future, and we'll fall into the curvature singularity if we're in the interior. It's in our future, so we'll get to the singularity. And as I said, the interior is similar to a collapsing universe. Now, there are many interesting classical properties of black holes. And the first classical property is the fact that perturbations, so if you take a black hole that is forms, after a little while, the black hole settles into a final form, which is given purely in terms of the mass, the angular momentum, and the charge. And all perturbations decay with a time constant, which is basically the time it takes light to traverse a distance proportional to the size of the black hole, of the order of the size of the black hole. With some constants, and for each black hole you can calculate by solving the equations, Einstein's equations around the black hole, what these numbers are, and they are called quasi-normal modes of the black hole. And you probably saw the LIGO announcement, and you probably have seen this plot of the black holes forming and the gravitational wave signal. This is not the signal, but this is the model that fits the signal. So the noise has been taken out, and this is the theory of what the signal should look like. And you see that after the two black holes merge, the signal rapidly goes down. So that's this exponential decay we just mentioned. Right? Now, second interesting, so this is the first interesting aspect of the black hole, that it settles into this universal form. The second is that the area of the horizon always increases. So you can, Hawking proved this just using Einstein's equations and the fact that the null component, the stress tensor, especially the null components of the stress tensor, are positive. And that's a property of matter. And another property is that in general, generically singularities are always behind horizons. And so the classical gravity theory fails, but the region where it fails is hidden to you by this horizon. So if you are sitting outside a black hole, so the black hole forms, there is something bad happening inside, but you don't see it from the outside. So from the outside, you have something very simple. You have this very few geometries that are characterized by mass, angular momentum, and charge. And so the result is very universal. So viewed from the outside, black holes are very universal and simple. That's the conclusion from this classical discussion. Of course, in the real astrophysical, black holes are more complicated. They have matter accreting, there is accretion disks, and much more complicated. But at least an isolated black hole is extremely simple. Now, let's discuss a bit the quantum properties. So the first surprise, well, the most important surprise is that the name was wrong. Okay, so black holes are not black. So that's the main lesson. Because black holes, quantum mechanics implies that black holes emit thermal radiation, and actually you can have white black holes. In fact, as a black hole gets smaller, it gets hotter, and you can have a small enough black hole that would look white. So in fact, the temperature of a black hole is related to its size by this formula, which is essentially saying that the typical wavelength of this radiation that is emitted is of the order of the size of the black hole. That's what this formula is saying. Now, for a black hole of order the mass of the sun, this is a very extremely tiny temperature, which we cannot measure. It's smaller than the temperature of the CMB by many orders of magnitude, so there is no hope of measuring this temperature. But they would imply that if the universe cools down in the far future, they will evaporate. Or if you have a small enough black hole in the beginning of the universe, it could be evaporating right now. I mean, they take a huge amount of time to evaporate. Notice that the temperature is very small, and so they're emitting very small amount of radiation. So I would like to explain why we have this effect. And to explain why, first we'll discuss a related effect, which is something that happens already in flat space, which is the fact that an accelerated observer moving in flat Minkowski space sees a temperature. Now, why does this happen? So this is a flat two-dimensional space, and we have the time direction here and the space direction. And we're going to imagine an observer who is following an accelerated trajectory. So someone who is accelerating. He has a rocket or something that is accelerating him or her and is following this trajectory. Now, this trajectory is the same trajectory that you would get if you took this space-time point and you acted with a boost generator around the origin. So the boost generator that generates boost in the time and x directions. Now, if we were to continue to Euclidean space, so we take this configuration, notice that for the accelerated observer, he sees a time-independent situation, in the sense that he's moving with constant acceleration and is feeling a time-independent configuration. Now, so we could go to Euclidean space, but if we go to Euclidean space, this boost becomes a rotation. So it becomes a rotation around the origin. And the rotation, this rotation angle is periodic. So after some time in Euclidean space, we come back to the original situation. And when we are in Euclidean space with a compact Euclidean time direction, we normally think that we have a temperature. In fact, if we have a temperature, we have to go in Euclidean time to a situation where we have a compact a circle in the Euclidean time direction. And we would get the temperature, so this observer would see a temperature which is proportional. The inverse temperature is the length of the Euclidean time direction, and it's just simply 2 pi r, where r is the distance from the origin. So here in the Lorentzian picture, r is the distance to the surface. This surface is a surface that separates, is a kind of horizon that separates the events that cannot send the signal to the accelerated observer from the events that can indeed send the signal to the accelerated observer. So r is the distance to this horizon. So this is an effect, it's usually called Unruh effect, and was first discovered by Bisoniano and Wichmann, who gave a derivation which is essentially the one I've given here. But many people didn't understand their paper, and so it took Unruh to rediscover the effect. So that's a lesson for you in the future, to write really clear papers. Now, the temperature is equal to the acceleration, or in units, this is in more natural units, there is some h bar and c. So you can say, well, normally we can accelerate, we get in our cars and we accelerate. Do we see a temperature? Now, the corresponding temperature for the case of ordinary acceleration is extremely tiny. It corresponds to a thermal wavelength of a light year. Okay. So it's a super, super tiny temperature. That's why we normally don't think about this effect. But certainly it's a very interesting effect that mixes together special relativity and quantum mechanics. Right? There is C, there is h bar. Now, this effect is also related to a feature of the vacuum of relativistic quantum field theories, which is the fact that the degrees of freedom that are making up this vacuum state are highly entangled, or are entangled. So if we have an observer who's moving here on the right along this accelerated trajectory, he can make measurements here on the right wedge and will not be able to receive any signal that is coming from this side. So that's the meaning of this horizon we were talking about here. So the observer has access only to one part of the system, and he is seeing a thermal state. a mixed state, and that's possible if we started from a pure state. If you start from a pure state and when you restrict to only one part of the system, you see a mixed state, means that you have entanglement. So we have entanglement between the degrees of freedom that live here on the right part, on the right wedge, and the degrees of freedom that live on the left wedge. And in fact, one can compute the entanglement entropy, and it turns out that it's infinite because of ultraviolet divergences when we get close to the horizon. Now, I should emphasize that this effect is a non-local effect. So you really need to be able to have Minkowski space all the way to the horizon in order to see this temperature. If, for some reason, there is a mirror here that is also accelerating, you might see the temperature equal to the acceleration, or you might sometimes see a lower temperature, depending on how you prepare your state. The statement is that if you have actually Minkowski space all the way to the horizon and a little beyond, then you'll see a temperature which is that given by the formula we've seen before. OK, so now we go back to the black hole case. So after having understood this feature of just ordinary flat Minkowski space, we go back to the black hole case. And we notice that this region in the black hole is similar to the horizon region that was separating the two Minkowski wedges. In fact, if we have an observer who's sitting at a fixed radial position in the black hole geometry, that observer would have to be accelerating. So that's not an observer who is following an inertial trajectory, geodesic. She is accelerating. And so we'll have an effect similar to what we had before in Minkowski space. So geometry very close to this horizon is just simply equal to the geometry of Minkowski space. And for the same reason we had that temperature in Minkowski space, we have it in the black hole case. And notice in the black hole case also, if we remain outside the black hole, we do not see the interior. And so we are tempted to interpret that also as entanglement entropy between the outside and the interior. Of course, the temperature for astrophysical black holes is too small for this effect to be detected, as we mentioned. So you might think it's an irrelevant effect. And you would be wrong. Now, but before talking about the relevance, let me point out that the black hole of a mass of a continent or about 10 to the 18 kilograms would actually look white. So it would be small. And so how big should the black hole be to look white? So the black hole emits radiation with a wavelength which is equal to the size, roughly speaking. So you should have a black hole that has a size comparable to visible light, right, for it to look white. Now, I said that this effect looks irrelevant for astrophysical black holes, and indeed it is. But in fact, there is one way in which we can see this effect. So it's related to the fact that the universe itself might be accelerating. And now the acceleration of the universe now is too small again for us to be able to see anything. But the early inflationary universe had a very rapid expansion, very rapid acceleration. Well, it had very high acceleration. And there this effect leads to something observable. In fact, according to the theory of inflation, there was a period of expansion with constant acceleration. And the classical theory of inflation produces a large, very homogeneous universe. So in inflation, in the same way as in the case of the black hole, any perturbation that you had in the initial state gets very quickly wiped out. All perturbations decay very, very quickly. And you get, at the end, a very homogeneous universe. And that was one of the reasons why inflation was introduced. But we don't live in a completely homogeneous universe. We live in a we live at long distances is slightly inhomogeneous, and of course at observable distances is very non-homogeneous. And the quantum fluctuations, which were produced due to this effect of the temperature, so the temperature in this expanding universe is equal to the acceleration of the universe, is equal to the Hubble constant during inflation. This temperature produces small fluctuations that then get imprinted into the shape of the universe. And at very long distances in our universe, those fluctuations haven't had a lot of time to grow. And we see their imprint pretty much as they were at the end of inflation. And so these quantum effects are crucial for understanding the large-scale geometry of the universe. And we are really seeing the temperature, the effects of the temperature of the very early universe. So going back to black holes, so the fact that black holes have a temperature makes us question whether they obey the laws of thermodynamics. So we saw the formula for the temperature of the black hole in terms of the size, where there is a precise coefficient here I didn't write down. And this comes from special relativity near the black hole horizon. Special relativity together with quantum mechanics near the black hole horizon lead to this formula. Then we have the relation between the size of the black hole and the mass that comes from Einstein's equations. And then we define the entropy using the first law of thermodynamics. That's what you would do if you had any thermal object in your lab. You would calculate the entropy by giving it some energy and seeing how it absorbs energy. And how the temperature changes as you absorb energy and so on. And from this you get the first law of thermodynamics. So use the first law of thermodynamics to get the entropy. And you find out that you can express the entropy in terms of properties of the black hole, and it turns out to be a very simple formula. It's just simply the area of the black hole horizon. So the black hole horizon has the shape of a sphere, and you calculate its area in units of the Planck length. So this combination of h bar and c is the Planck length, and that is the entropy. And Bekenstein, even before discovered the radiation, found this formula for the entropy. And in fact, there is the classical increase of the area of the black hole can be interpreted as the second law of thermodynamics. Now, there are a couple of puzzles that arise with black hole thermodynamics. The first is that is a black hole as seen from the outside the same as any other quantum system? So if we are sitting outside, we have this object that, so we throw matter in, it grows, it has some temperature, the matter comes back out in thermal radiation. Now this happens with many things, many objects that we can have in our lab. We can have a glass of water that we heat, it gives off radiation and so on. So does a black hole as seen from the outside behave as any other quantum system? In particular, is the entropy the log of the number of microstates? So can we think of the entropy as the statistical entropy, as arising from microstates that we are not directly accessing? Is the evolution of these microstates consistent with unitarity? And also another question is whether this is consistent with the interior. This is a question which goes beyond the black hole as seen from the exterior, but it's also an interesting question we'd like to ask. And there is a lot of evidence that the answer to these two questions is yes, and we're still confused about how this is consistent with the interior. So one question is, can we replace, for example, a black hole by a collection of qubits, so that any experiment done from the outside would find them indistinguishable? So that would be modeling the black hole in terms of a quantum system, so that any experiment done from the outside would be reproduced. Asked in another way, so suppose someone tells you they have a black hole in a bottle, and all you can do is send stuff from the outside and watch what comes out. Can you tell that this person has a black hole or not? Now, this system, quantum mechanical system we are looking for, should have some gross features. So it should have a large entropy, because black holes, when they're well described by classical physics, they have a size much bigger than the Planck length, so they will have a large entropy. And it should have a very small energy gap, almost continuous spectrum of radiation. It should thermalize fairly quickly, so we saw that things decay pretty quickly. And also, the information that we send in should get scrambled very quickly. Scrambled means that it should be spread over all the degrees of freedom of the black hole fairly quickly. This we'll see more later, what it means. And of course, these are some gross features, but of course we can ask about more detailed behavior of the decay of perturbations, where they match the result we get from Einstein gravity and so on. So for this we can use a quantum the relationship between quantum systems and gravity. You can call it the quantum gravity duality. And for certain specific quantum mechanical systems, there are quantum mechanical models. There is a precise relation between black holes and the quantum system. So for example, just as an example, you can consider a collection of harmonic oscillators and Majorana fermions or fermions with specific interactions. And that will give rise to a black hole in 10 dimensions. So how weird is this system? So let me just give a little bit of a flavor of what this little model looks like. So it's a quantum mechanical model. There is time, only time, and it has harmonic oscillators. So these are ordinary harmonic oscillators, and also has fermionic oscillators, or fermions. So it has some bosonic and fermionic degrees of freedom. And it has some interactions. Roughly speaking, the interactions are between the fermions and the boson, and also there are some self-interactions among the bosons themselves. Now, all these interactions are consistent with certain symmetries that we take the system to have. And we take the symmetries mainly for convenience, because this is a model we can analyze and for which we can actually say what the gravity dual version is. And it is basically what I said, except that there is a whole family of harmonic oscillators indexed by an index that goes from 1 to 9, and another index that runs over all the values of the adjoint representation of un. Or more precisely, you can think of these harmonic oscillators as a matrix of n by n elements, and each element in the matrix is a harmonic oscillator. And all the interactions are consistent with the un symmetry. So that's why it's convenient to group the oscillators in this way, so that you view them as n by n matrices, and then all these interactions are just simply products of matrices. So the interactions have very specific form among these oscillators. And all the interactions are fixed by this un symmetry, and also another symmetry of this model that relates the bosons and the fermions. So that fixes all the coefficients. And really, we don't know whether these features are fundamental or not. We think for finding a particular duality or particular example, we needed to make these assumptions, but we don't know what the class of models that has a gravity dual, as I will mention, will be. So the geometry has the following rough form. So there is a radial direction, and there is a time direction. And when we consider the system at finite temperature, there will be a horizon. So there is a region outside the horizon. The whole geometry is actually 10-dimensional. So it has this radial direction and the time direction plus some directions of an 8 sphere. And the curvature radius over the Planck length is of order n to the 1/4. So when n is very large, so when we have a large number of oscillators, we find that the curvature radius in Planck units is very large. That means that the solution is weakly curved. And actually, to be more precise, the curvature of the solution varies between the horizon and the boundary, and gets to be a little bit high here near the boundary. So the gravity description is correct for some regimes of temperatures. And we can calculate, using this gravity description, for example, we can calculate the entropy and the free energy as a function of the temperature. For that, we simply use the, let's say, Hawking-Bekenstein formula for the entropy as a function of the area of this black hole. And in that way, we can calculate the free energy. And then we can compare to a direct computation in the quantum mechanical model. So you take this quantum mechanical model, which contains bosonic and fermionic oscillators, and you just compute the entropy there. It's non-trivial. You need to do it with a computer, and it's somewhat difficult to do. And you find the following. So the gravity as a function of temperature, the gravity theory gives you this curve. Okay? And the computer simulations give these dots that are here, right? And well, at first sight, it looks, you would say, oh, they disagree. They don't lie on this curve. Now, what's important here is that at low temperatures, which is when it should agree, they tend to lie on the curve. The computation gets progressively harder as you go to lower and lower temperatures, because the interactions grow in this model. But you can understand the origin of these corrections even from the bulk point of view, which have to do with the fact that the bulk theory is not purely Einstein gravity, but it's Einstein gravity plus some stringy corrections, so corrections due to string theory. And so the dual of that model is not purely Einstein, but the whole string theory. And once you include the first string correction of string theory, you find some formula that agrees a little better. Of course, as you go to even higher temperatures, it starts disagreeing again. You would have to include further corrections. Yeah.
The t, how are we supposed to simply think of 0 to 0.9 for t?
Yeah, so I didn't say, but so this model has some dimensionful constants, right? So interactions have some dimensions. So this t is the temperature in units of the interaction strength, which has some dimension. Sorry, I should have explained that. So maybe I'll explain it better for the benefit of everyone. So this model is such that at very high temperatures, the interactions become very small, and the model is almost free. So at very high temperatures, you can view it as a free collection of harmonic oscillators. So there, the computation of the free energy is very simple, and it does not agree with gravity or even gravity with small stringy corrections. Okay. At low temperatures, the interactions become stronger, and then the computations agree with what you can compute using gravity. At very low temperatures, we expect them to agree very well, but they are hard to do and they have not been done. So they have only been matched up to these intermediate temperatures. Now, so in the gravity picture, I briefly said that the curvatures become very high when you get near the boundary. And so as you raise the temperature, the horizon goes closer to the boundary, and then you cannot calculate anymore. So you can calculate only when the horizon is far away from the boundary, that is at low temperatures. In those cases, you can calculate using Einstein gravity. So this is a generic feature that the Einstein gravity description will be valid when the interactions are very large. Now, I mentioned the strings. So the relationship between these models in terms of matrices, especially these matrices with the UN symmetries or where the UN symmetries are gauged, and strings is an old story that was originally discussed for quantum chromodynamics, so the theory of strong interactions, but it's actually true for any theory of matrices. And the idea is that if you take, so in chromodynamics where you have three colors, so the gluons are 3 by 3 matrices, you can take n instead of 3 and the theory simplifies. And in fact, any theory which involves n by n matrices is supposed to simplify in this way, where the gluons, which can be viewed as objects that have two indices, a matrix having two indices, form chains, which are sort of like necklaces. And these necklaces behave very much like strings. So when the interaction is very strong, they behave like continuous strings. And closed strings are glue balls, and so that's in QCD. And the coupling between these different strings goes like 1 over n. But this, which was argued in '74 for QCD, is actually supposed to be true for any model, including this quantum mechanical model I just mentioned. So in these models, we can imagine we have these spins localized in some region that are all. So these spins, roughly speaking, are trying to symbolize those harmonic oscillators that we have, the bosonic and fermionic harmonic oscillators. And at low energies, when interactions become effectively strong, we see some emergent geometry that is 10-dimensional. So this geometry somehow is not directly related to the geometry of our own space. So we have our own space, which is 3-dimensional, and we have all these spins. And at low energies, we have this emergent 10-dimensional geometry. Now, in what cases do we know that we can have geometries coming from these quantum degrees of freedom? So we need at least large n. So n should be the number of spins that you have, should be, or qubits should be very large. Also, we need very strong interactions. And typically, these interactions have to be of the type of all with all, or have some structure roughly like this. So if interactions are confined only to nearest neighbors, then if all these spins are arranged, for example, along a single line, and interactions are among single neighbors, then you typically will not get a gravity dual, unless you have lots of qubits per unit length, let's say, and you have then the possibility of having lots of interactions of all with all. Now, what are the lessons that you extract from these realizations of geometries in terms of qubits? Well, the lessons is, the first lesson is that you can have an explicit realization of the microstates. So you can have a set of microstates, so in this case, for example, of the spins, so we can have, or the harmonic oscillators, you can have a set of harmonic oscillators, bosonic and fermionic, whose entropy agrees with the entropy of the black holes. So that matching of the free energy I mentioned is the same as the matching of the free energy, of the entropy. And the description in terms of the qubits is perfectly unitary, so this would be a description of the black hole as seen from the outside. Now this matching of the entropy, which here looked very coarse and almost marginal, in some cases can be shown with great detail. That's the case in the case of extremal black holes, where you can consider special supersymmetric systems, and which are related to supersymmetric gravity theories. And you consider in them charged black holes and take the extremal limit. So charged black holes have a constraint that the masses should be bigger than the charges in order for the horizon to be smooth. And there is the extremal limit corresponds to the mass equal to the charge, and that also has zero temperature. And in these cases, you can count the states using sophisticated techniques that have been developed for supersymmetric theories. So here we're using, one it uses supersymmetry to understand, to be able to count the states very precisely. And well, this was done many years ago by Strominger and Baffa, and then it was done in more detail by many other people, including people listed here. And it's a field that continues today to compute it better and better. And what was found is that the entropy is not just the area, but it's the area plus corrections. And these corrections can be interpreted as quantum corrections that you get in the gravity theory. So the entropy is the leading term in some expansion, where you also should include quantum mechanical corrections. And there is a very detailed agreement between these two ways of computing it. Okay, so now we return to a bit the discussion of entanglement. And we said that the thermality Minkowski space is due to the entanglement with the region behind the horizon. And so we can ask what happens with a black hole, or whether we have something similar for a black hole. So now we're going to consider, instead of considering these black holes that collapse, we're going to consider another kind of black hole. We're going to consider essentially the Schwarzschild solution that the solution that Schwarzschild wrote in 1916, but which was understood really better in the 60s, especially by Kruskal. So there was gradual understanding of what the solution looks like. And first it was found that this horizon, there's a region behind the horizon, and then it was found that there is this other region. And eventually, the whole picture is this, where we have a solution of the vacuum Einstein equations. There is no matter anywhere, but the solution, the geometry looks a bit weird. The geometry has an exterior, so it looks like the outside of a black hole here. So this whole region looks like the space-time outside the black hole. So we have here asymptotically flat space, so we have flat space far away. Then this is the black hole horizon. And this region looks like another black hole. So this also region looks like far away in four-dimensional Minkowski space far away. But these two black holes are connected through the middle. So the horizons are touching at this point, and they are sharing a single interior. These two black holes share a single interior. So this is the simplest solution of Einstein's equations. It was the first exact solution of Einstein's equations. And we would like to understand a little better what it means. Now, before, here we had two black holes in two completely disconnected spacetimes, but we could consider a related solution. It's not identical to the previous solution, but it's close to the previous solution, where the two black holes are actually in the same spacetime. So we have two black holes far away, but the geometry is pretty funny, and they are connected through the interior. So this is a weird geometry that you can consider and you would like to understand. Now, if you find two black holes in nature produced by a gravitational collapse, they will not be described by this geometry. They will be described by the previous geometry we discussed that contains a single interior for each black hole. But let's analyze this geometry. You can view it as a weird configuration that the gravity theory allows, and try to understand it. Now, a curious feature of this geometry is the following. So these two black holes could be very far from each other. So one could be here, and the other black hole could be in the Andromeda galaxy, so millions of light years away. Now, if you have a person standing here 1 meter from this horizon, and you have another person here standing 1 meter from the horizon of the other black hole, they are separated by millions of light years through the space, but they're only separated by 2 meters through the wormhole, so through the connecting space here between the two. Now, you might think that since they are separated by such a close distance, they could just travel from one side to the other. But this is not possible because as a person here tries to travel to the other side, well, what can one do? One can try to travel, and one would just move along a time-like trajectory here. So one cannot move along a horizontal line because that would be faster than the speed of light. So one has to move, let's say, in this direction, and one will end up with at the singularity. Now, singularity occurs because the sphere is shrinking to 0. So what is happening is that the wormhole mouth was open at this instant in time, but it shrinks as you go to the future. Or equivalently, you can say that these two horizons we are touching at this point, but then they start separating from each other, and they separate so fast that a person here can never catch up and go out. So these wormholes are non-traversables, and you cannot send signals, and there are no causality violations in the ambient spacetimes when you have such wormholes. So these are not the wormholes of science fiction. Okay? So in the wormholes of science fiction, you can travel through the wormhole and travel faster than the speed of light. These are the wormholes of general relativity, okay? With positive energy conditions, with the matter and the energy conditions that we think matter obeys. And this is good. I mean, Einstein's theory of relativity is based on the idea that you cannot propagate signals faster than light. It would be funny if by considering the theory itself, you can construct configurations that that allow sending signals faster than light, right? It would be like the theory itself proving inconsistent somehow. The fundamental assumption of the theory was not true. But it's interesting that it is not possible due to the fact that energies have to be positive. So especially null energies have to be positive. So energies along the null direction. Or if you wish, energy minus momentum has to be positive. So if you go in, you cannot go to the other side. Now we can consider now these black holes that occur in these gravity duals. So these two systems of spins that we were discussing are harmonic oscillators. And we can consider in that case also geometries that are connected. It's the same type of geometry we discussed in flat space. And the idea is that in those cases, this geometry is described by considering an entangled state in these two non-interacting quantum systems. So we have two systems of harmonic oscillators. They do not have any direct interaction between the two, so the Hamiltonian does not connect the two. But we constructed a state that is entangled. So in this case, so we have this geometric connection. We think that the geometric connection arises purely due to the effects of entanglement. That we think is true for this particular entangled state, which is called the thermophile double state. And this is a feature that was initially noted by Israel in general. So he noted the similarity between the extended Penrose diagram and the thermophile double state. And in the context of gauge gravity duality, it just simply translates into an entangled state in the boundary theory. So the idea is that if you have these systems of qubits that are entangled with each other, then they will be connected through the interior. Now, just to explain more clearly how weird this is, let me just tell you a little story. So far in the future, there were two people. There was Romeo and Juliet, okay? And their families did not want them to meet. So they put one in the Milky Way galaxy and the other one in the Andromeda galaxy. But they are very clever, and they construct a pair of entangled black holes, right? And they synchronize their clocks and so on, and they then they decide to jump into their black holes, right? To their respective black holes. Now, so they jump in and they can meet in the interior. Then they'll die, so that's too bad. But they can meet before they die. Now, what do the people from the outside see? So their families see that Romeo jumps into a black hole and commits suicide, right? And Juliet also commits suicide, right? So according to their families, it ends like in Shakespeare's play, right? But they actually met in the interior. So that's the part Shakespeare missed. So the question is, how do we describe this? So this is something that we think it's true by combining what we know from black holes and gauge gravity duality, and by what we know from solving the equations of general relativity. But how do we describe this meeting? How does this occur in one field theory, in one quantum system, or in the other, in the combination of the two? Exactly how does this happen? How should we describe the interior? Now, all these are questions we don't know a good answer to. So we have different theories, and there are almost as many theories as people working in this field. But we think that answering better these questions will teach us something about how quantum gravity works in general. So, so the interior seems to be intimately connected to the entanglement between the two systems, and it's something that seems to be happening out of these ghostly features of entanglement. So out of the ghostly features of entanglement, we are getting a solid geometric connection between the solid spacetime that that those Romeo and Juliet will experience when they jump into their black holes. Now, so the fact that the connection implies that you have entanglement was noted by Israel, and then Van Ransdorff proposed that perhaps whenever we have entanglement, we might get some kind of geometric connection. So we call this ER equal to EPR, Einstein-Rosen bridge, which is the fact that the two black holes are connected, that the Schwarzschild black hole has two connected. The maximally extended Schwarzschild black hole describes two connected black holes through the interior. That's called the Einstein-Rosen bridge. That's the same as EPR. Now, there has been some interesting interplay between some techniques people use to describe quantum systems that are strongly interacting, which are called tensor networks. And these are some techniques to represent the wave function of a complex system in terms of simpler parts, in terms of, and typically the wave function of a system that can contain many qubits can be expressed in terms of some kind of networks of tensors of how you basically contract indices in some space to construct the wave function. I'm not giving you all the details, I'm just telling you the basic idea. And if you think of the networks directly as the geometry, then it definitely realizes this idea that whenever you have entanglement, you have a geometry. But of course, we just simply define the networks as a geometry. We are not showing that these geometries obey Einstein's equations or anything like this. So, but this is one interesting idea that is being actively explored. And there have been many recent papers going in this direction. Some of these papers by Daniel Hallroth, who's here in the audience. Now there are so let's now discuss, well, I think I might have run out of time to discuss another aspect of horizons. I think I started later. When is the clock stopping? Time goes on forever, right? Or
5 or 10 minutes.
Yeah. So I'll discuss just a short, very quickly, a connection between chaos, complexity, and black holes. So it's common that thermal systems appear to lose information. So that's very common. So if you throw, a drop of ink into the water, it will dissolve and so on, and you don't know where you dropped it after a while. And the dynamics of a black hole also seems to be very chaotic. Now, one way to characterize chaos is to think about doing small perturbations on the system. So let's call one small perturbation, inserting some operator W. And then we can consider an unrelated small perturbation on some other part of the system. So in the case of the black hole, it could be, let's say, sending a little wave from one side of the black hole and a little wave from the other side, for example. So initially, these two perturbations, if we do them at the same time, they commute. There's two operators that commute with each other. But if we let one evolve, then it creates some disturbance on the black hole that affects all the degrees of freedom. And then after a while, the commutator will typically be 1. And the while is not very large. It's just simply a time which goes like the logarithm of the entropy. So it's a time of order beta. Beta was, again, the size of the black hole, roughly speaking. And the logarithm of the entropy is just the logarithmic in the entropy. So it's not a very big number. And it turns out that this growth of the commutator is related to the growth of scattering amplitudes at the near horizon region when you perform a large relative boost between the waves created by one and the other. So let me just explain it in more detail. So if we, let's say we send in a wave here created by this operator, and we compare it with a wave that will be received by this other operator W of t here later. Now, if we wait a long time, it means that since time translations here in this region, remember we said that there were more or less like boosts around the origin. So those were like the time translations of an accelerated observer in Minkowski space, and those were like boosts. So these two particles will be very boosted relative to each other. That means they will collide with large energy. Right? And the gravitational interactions grow with the energy, and so these interactions become large, and that's why the commutator becomes large. And in fact, one can derive a general bound on the growth of this commutator. So a commutator grows exponentially as a function of time with a prefactor that is essentially the temperature. Okay? And this is something that was initially derived for black holes, but in fact, you can argue that it's true for any system that contains a large number of degrees of freedom, suitable to some according to some very general assumptions. You can show that this will be an upper bound on the rate of growth, and any other system will see a growth which is slightly less than that. So, or well, might be less than this, but not bigger than this. So this is a kind of Lyapunov exponent. Showing the divergence of classes. And it's an analog to the Lyapunov exponents that talk about the trajectories, the divergence of trajectories in classical systems. So this is a quantum analog. So as conclusions, we see that black holes tie together very different fields of physics. And if we want to understand black holes, you have to learn about all these fields and how they interrelate. And there are some things here we can't understand yet that are behind the black hole. But once we understand the interior well enough, we'll probably understand quantum spacetime and quantum geometry better, and we'll perhaps be able to apply those things to gravity and so on. So before I finish, I'll say some words about the next 4 lectures. So lectures 1 and 2 will be an introduction to the gauge gravity duality for non-specialists. So I'll try to be very basic and elementary. And assume very little background about string theory and so on, as little as possible. And then the lecture 3 will be more about entanglement and geometry. And lecture 4 will be a bit more about what we just talked about the last couple of transparencies. Thank you.
Take 2 or 3 questions.
Yeah.
All right. So, saying you have a tennis ball.
Yeah.
You've got your black hole.
Yeah.
And you throw the tennis ball
Right.
into the black hole.
Yeah.
What are the characteristics of what happens to the tennis ball as it enters the black hole
Right.
and begins to become compressed?
Right. So, so the tennis ball. So let's first describe this from the tennis ball perspective. So the tennis ball falls in, sees the tidal force is increasing. When it crosses the horizon, doesn't feel anything particularly special. And when it gets to the singularity, it's ripped apart by the tidal forces. Okay? So that's from the tennis ball perspective. From the point of view of the outside perspective, the ball falls to the black hole horizon. And according to the classical description, the tennis ball gets more and more redshifted. So the light from the tennis ball, instead of being yellow, so it turns redder and redder and redder until you don't see it anymore. Now, if you include the quantum effects, at some point, the tennis ball light will become comparable to the size of Hawking radiation. At this time, we would say the tennis ball is melting in this hot atmosphere of the black hole. Right? So that's the perspective from the outside. These are the two perspectives of what happens to the tennis ball.
It essentially dissolves.
Yeah. So in one from the outside, it looks like it dissolves when it approaches the horizon, and from the interior point of view, from the tennis ball point of view, well, it breaks up when it reaches the singularity. So from the interior from the tennis ball point of view, the tennis ball lives a kind of afterlife, right? So the tennis ball doesn't die when it reaches the horizon, but a little later. And the question is how to describe this afterlife, and what the evidence is of this afterlife from the outside, for example, or whether we can even describe it.
I've been curious about what is it that allows the event horizon to form in a finite amount of time? When the body is collapsing in the first place.
The thing is that the event horizon is an imaginary surface. And in order to know where it is, you need to know what the final state of the black hole is. So you say, well, the black hole has formed and so on. And after it forms, you say you look at which light rays can escape and which light rays cannot. And you draw a surface that divides the two. And that's how you can extrapolate it backwards, right? So an observer who is falling in there, it has no way of saying that he or she is crossing the horizon.
From an outside observer, though.
You know, if you're just outside watching a collapse.
Yes. Yeah, what you see is
how do you? I mean, I just don't understand what's going on.
The outside observer sees things slowing down. So sees the matter that is falling in, and sees all this matter slowing down and being redshifted, sort of like falling through this gravitational potential well. So we saw that the clocks. So in one of the first transparencies, we saw those clocks almost stopping when you reach the black hole horizon. So that's roughly what is happening to matter falling in. The clocks almost stops. And it gets redshifted. That effect is the same as the matter being redshifted. You see it less and less and less until it gets dissolved into the Hawking radiation cloud.
Not to take up too much time, then. So where would I look to get a more detailed explanation? Because it sounds like you're saying the event horizon never forms from the perspective of the outside observer, but that doesn't seem to be consistent. So I'm just wondering if I can look elsewhere for further information.
No, I feel so the event horizon is a property of the whole space-time, and it's what divides the interior from the exterior. The interior is all space-time points that cannot send the signal to the exterior. So that's the definition of the event horizon. Okay. So once you solve the Einstein's equations, after you solve them, you can figure out where the horizon is. And it's a global property of space-time. You cannot say locally where it will be.
So you have a contradiction between a classical black hole and a quantum mechanical black hole. And your description is that when something falls in, it's looking like a classical black hole to the entity that falls in. When does it become quantum mechanical? How close to the singularity?
Well, the idea is that the black hole is always quantum mechanical. So from the outside, we see these effects of Hawking radiation, but we don't think that these quantum effects that give rise to Hawking radiation do anything to the observer that falls in. So when the observer falls in, he or she does not see these effects as doing anything bad. In the same way that when we look at if we looked at the flat space as a person in flat space, right, that is accelerating. Remember that plot? Should I find it? Let's see. So if we look at this person who's accelerating in flat space, Then for this person, this surface is very special, right? So anything that is very close to this surface is very, very hot, right? All the degrees of freedom near the surface are very hot. But if you are someone who's, let's say, traveling along a time-like trajectory, just sitting at a fixed position x, right, moving this way, right, you would just cross this surface and nothing special would happen to you, right? So that's what we think happens at the black hole horizon. So that when the matter is falling through the black hole horizon, you don't feel all this quantum.
So when from the observer, from the inside, does it become quantum mechanical?
Oh,
or is it always classical?
For the observer falling in, there are big quantum corrections when he or she reaches the singularity. There, the tidal forces become very large, and quantum gravity effects would become very important.
So that's when it happens. That is, as you go approach.
That's when it happens from the point of view of the interior person. So the description from the outside and from the inside are radically different, and trying to match them together is a central problem.
Okay, let's thank Juan and.